So maybe let's get started. Welcome everybody to this Theoretical Astrophysics Colloquium, and it's really a pleasure to have Floor Broekgaarden here. Floor did her bachelor and master's in Amsterdam, where we first met and started working together. And then she took a gap year and traveled in many places, including Australia, where she digged deeper into gravitational waves that she was already doing her bachelor's and master's, and then moved to Harvard for a PhD, where she also became a quai of this Astro AI Institute that is behind her head right now. And and after that, she became a Simons Junior Fellow in New York City at Columbia and at CCA. So we found each other again, basically professionally. And she will start as an assistant professor at Johns Hopkins University next year. And the floor is all yours.
Yeah, thank you so much for that introduction. So my talk, I will hopefully tell you all why, for me, massive stars are truly the dinosaurs of our universe. Because similarly to how paleontologists actually can use fossils to study the lives and deaths of dinosaurs, I use the fossils of massive stars, which are black hole collisions, to understand how these massive stars once formed, lived, and died throughout the cosmos. Okay, so how does that work? Well, compared to our sun, shown here, these massive stars that I'll be talking about are these stars that are about 10 to 200 or more, the size and mass of our own sun. And they're very special. They're very rare. They live fast and die young. So a typical massive star has a lifetime that's 1,000 times shorter than our own sun. And they're also extremely rare in our universe. So typically when you form 1,000 stars, only one of those stars actually is born as a massive star. And so combined, this makes them extremely rare in our universe among stellar populations. And so it's quite tough and difficult to observe and study large populations of massive stars and understand their lives. And this is true for our own Milky Way, where we often rely on these very expensive surveys, such as Hubble surveys. But it's even more true for more distant galaxies to understand individual massive stars in those galaxies. It becomes almost impossible. And so as a result, there's actually very little that we still know about these massive stars. But there's one thing that we do know about them, and that is that they play an extremely important role in all these different physical processes throughout our universe. So for instance, they trigger and trace star formation. They provide a lot of feedback in our universe and galaxies. They form these explosive and energetic transients, such as X-ray binaries or supernovae, and they often outshine galaxies. They often perform the most light in galaxies, especially early in the universe. They also are thought to be an important source of reionization. They produce some of the most heavy elements in our universe, such as oxygen, all the oxygen that we breathe probably comes from these massive stars. And last but not least, and maybe most important for me, they form these compact objects, black holes and neutron stars. Now, one other cool thing about these massive stars is that they often or almost live in pairs of stars. And these massive stars, when they are formed and live in a pair, they can actually undergo all these interactions. They can exchange mass between the two stars and have interactions. And by the end of these lives, when these massive stars die, they actually go supernova and explode. Now, I didn't have the same budget as Interstellar, so instead, I visualized them with these marbles, black holes. And so if these two stars can survive all these phases, all the interactions, explode, and the other star can explode, and they can stay together, which is extremely rare for these pairs of stars. In most cases, they disrupt. But if they can stay together, they can actually form these pairs of black holes that then over billions of years can eventually spiral in and collide, forming a slightly bigger black hole. Now, this is exciting because as of 2015, for the first time, we detected gravitational waves, and we actually observed the collisions of such black holes by LIGO and Virgo. And since that time, scientists have been wondering, okay, so if we're seeing these collisions of black holes, can we actually use them to understand and study massive stars in the past? This is what I and many other people in this field call gravitational-wave paleontology. So understanding how massive stars form and live from these new black hole collisions that we can now observe today. Okay, and so how do we observe them? Well, now we know that everywhere in the universe, there are these black hole pairs that eventually collide and then produce these waves in space-time itself that travel for millions of years through the universe until they eventually reach us here on Earth, where they cause these like wiggles in Earth itself. Here, vastly exaggerated. And these wiggles we can pick up with these ground-based interferometers, such as LIGO shown here, based on like laser interferometers, where these small wiggles will form a little inference pattern. And from these collisions, we can actually infer different properties of the black holes, such as their black hole masses, a bit of their spins, mass ratio, et cetera, et cetera. And there's one really cool thing about these black hole collisions that makes them in particular really, really special to study massive stars in the past. And it has all to do with cosmology. So if you imagine that this is kind of an artistic picture of what our universe looks like, this is where the Big Bang happens. And then basically here's where the Earth is at redshift 0. The special thing about these black holes is, if you picture this, is that the stars maybe formed very early on, and within just a few million years formed pairs of black holes. But these pairs of black holes in their galaxies can like actually be rotating and get closer and closer together over many gigayears. So the place where they actually collide is at much higher redshift, like a much lower redshift, like much closer to us today. And that also means that the gravitational wave sources and the black hole mergers that we're seeing today with LIGO, which can only kind of reach up to redshift 1, might already probe stars that form those black holes as high as like redshift 10 of first star formation, possibly even higher. And that's just because this delay time, so the time between when the two stars formed and the actual black hole collision, can span many gigayears or even longer. And at the same time, this makes it a challenge because it also means that the black holes that we're seeing today might actually come from this like mixture of stars that have formed throughout the universe, kind of making it more puzzling to understand like how did they actually form. And so as a result, it's actually not so easy to just go from a black hole collision observation immediately to the massive star, because we don't directly measure actually the properties of the stars when we observe a black hole collision. You can kind of compare it to how when you see a fossil, you can maybe not immediately say or tell whether the dinosaur used to have feathers. But instead, what you might do is you have a population of dinosaurs that you model with and without feathers, and you forward model it to see if they leave behind different fossils. And so in practice, in gravitational wave paleontology, we do the same. We actually have to like forward model populations of stars at these different redshifts when they formed to see what kind of black hole collisions do they leave behind and what are the properties of these black holes that they leave behind. We then compare that to observations to test these models. And so in practice, this often looks something like this, where we have some machine or code that we call rapid population synthesis models that we give like different binaries, different pairs of massive stars with, for instance, different masses as properties. And then this calculates the outcome of the evolution of those two stars. And it, for instance, will say, yes, this one formed a binary black hole merger, or in other cases, it'll say, no, this one, the supernova went off and it disrupted. Which is nice. And in practice, it maybe looks a little bit more like this, where we have some code. In this case, Compass is one of the codes I worked on. You give it like a binary with different initial conditions, and it takes into account all these like single star evolution, and as well as like binary interactions like mass transfer, supernova explosions, and then tracks the evolution of the binary over time and decides whether it forms a gravitational wave source or not. Now, the nice thing is that these are rapid codes, so we have optimized them and often use like parameterized prescriptions instead of like solving all the equations ourselves. And by doing so, these codes are very, very fast. So they can typically calculate the evolution of a single binary under like a second. So in less than a second, we can calculate the evolution of one single binary and decide, does this binary at these initial conditions make a gravitational wave source, yes or no? And so you might say, well, okay, problem solved. We have this rapid code that can evolve these stars, calculate whether it forms a gravitational wave source. We're all done. Well, not so fast, because even though these codes are very fast, we still are limited by a computational challenge and the computational cost of these simulations. And this is because of something that I call the uncertainty challenge, or gravitational wave paleontology uncertainty challenge. And this is basically that when we're doing this process of forward modeling these stars, that we run over these 5 different barriers. Each one that gives us like a huge computational cost of these simulations.
I can do it from here. Mute all, or no, we don't want to.
It should be good. Everybody's muted but you. That's the room. Host Arizona. I think that's the room.
The desktop mouse has to close this.
This thing.
Oh,
Sorry.
I mean, it might be nice to have it.
Thank you.
So we basically are saying there's these 5 different barriers that we have to overcome that each drastically increase the computational costs of doing these simulations. So let me talk you through them. So the first one is that we're actually not entirely sure how these black hole collisions and black hole neutron star and binary collisions exactly formed. And there's different theories out there that might explain their formation pathway or formation channel. And these are all like listed here. There's even way more, but often they're categorized in kind of these boxes. To give you the first example, the first one is, for instance, maybe they come from these pairs of massive stars that I mentioned that start very white. And in that scenario, the evolution kind of goes as the following. You start with a very white pair of massive stars, that then evolves, like the first star evolves the fastest, grows in size as it like becomes a red giant, and eventually initiates a mass transfer episode where mass can flow from this star to the companion star. This eventually ends and it forms this like helium star, but still its companion star. Then this star will eventually go supernova and form the first compact object in the system. So now you have a black hole star system. The other star then also evolves. Maybe there's like a short X-ray binary phase, and then it also enters a mass transfer phase, but now this is unstable and so fast that star cannot respond. And instead, it's basically the compact object is like engulfed in this envelope, and we call this like a common envelope phase, where the black hole, due to drag, can get much closer to the star and hopefully in the end like eject the envelope from the star. And what you end up with, if successful, is this black hole strip star system that's much closer in separation. If it survives all of these, the second star can also go supernova and form the second compact object, like either a neutron star or a black hole. And then these 2 compact objects can spiral in and form the gravitational wave source. Okay, so this is one formation channel, but there's many, many more possible ways of forming these pairs of black holes. So for instance, they can form from these population 3 stars, the very first stars in our universe that basically have no metallicity. They can come from triples or quadruples or multiple star populations, where you basically have a 3rd or 4th object that can help the stars get closer together. Or maybe they form in this like completely different way, these like dense stellar environments, where you have many, many stars or compact objects going through n-body interactions, like 3-body interactions, pairing in and out, and eventually getting a very, very dense or close compact object system. And each of these channels come like with their own specific like imprints on the black hole population, the merger population. But as a result, what we truly should do is like rerun our simulations for all these different formation channels, making it already like much more complex and much more computationally expensive to do this. The second challenge is that we actually are not entirely sure about the initial conditions of stars and which stars form gravitational wave sources. So in practice, we don't have to just try different masses of stars, but also different eccentricities, different metallicities, different like initial periods, etc., etc. And it turns out that this is actually very important because, for instance, some of these initial conditions can have a drastic impact on the outcome of the binary system. So for instance, here's a plot that shows, depending on which metallicity you start with in your binary, so the amount of metals in the star, you get very different outcomes for the total mass of the binary black hole merger in the system. And so as a result, we shouldn't just like explore these two initial properties or conditions or axes, but like try all these different axes of initial conditions. And this just means in any simulation that you really increase your parameter space and thus increase your computational cost as you go. The third challenge and barrier is that these gravitational wave sources are extremely rare. As I said, most stars that you start with will actually disrupt during one of the supernova explosions. And so in practice, in our simulation, often only when you simulate like 1 million binaries, maybe only one or a few actually become a gravitational wave source. And this is both true in like our simulations, but also probably in the real world. Like it's very rare outcome to become like a gravitational wave source. And this means that if you don't run your simulation long enough, that you can actually get some of these like Poisson uncertainty statistics. Just uncertainties from only having very few samples in your simulation. But if you had run your simulation for longer, you have more gravitational wave sources. And so it's easier to make like distributions and statistics. And so again, we have to like rerun their simulations, but like run them for much longer because of these like small number statistics in our simulations. The fourth and fifth barriers are maybe the most important. The fourth one is that I showed you like an example of the evolution of a star, but you probably noticed that there's a lot of different phases in this stellar evolution. And all these different phases come with enormous uncertainties. We're actually not really sure how each of them work because we don't have that much data of massive stars, and especially of these short-lived phases like mass transfer. And so in practice, what we do in these simulations is that we have kind of knobs. But like we parameterize these phases like mass transfer and then have like a knob or a free variable that we say, okay, we can vary this between 0 and 1, for instance, for how much mass there's transferred during a phase. And since we don't know the real number, we rerun our simulations trying different values for some of these like hyperparameters. But in practice, what this means is, again, we have to rerun our entire simulations, calculate our populations, to understand how these uncertainties and different assumptions can lead to different outcomes and different imprints on our simulations. And last but not least is that binary evolution and stellar evolution is really uncertain. And so one of the other things is that often much of our physics, such as this common envelope phase, is often described by these parameterized prescriptions. So this is a simple equation with like 2 free parameters here. But in real life, we know from hydro simulations that these phases are probably much more complex. So here's like a hydro simulation of the common envelope phase. And so what we should truly do is like replace some of our like parameterized prescriptions by these more detailed simulations. But that becomes very expensive because maybe our parameterized prescription took like a second to calculate, whereas like these simulations can often take like weeks or 2 weeks or longer for a single system. So it becomes very, very computationally expensive. And so together, all 5 of these barriers basically mean that to overcome them all, it would be way too computationally expensive. You would end up with computational times that are like way more than 100 of years for all the simulations that you want to do. And so it's basically infeasible to do them all. And so all current simulations and research pays a high price by usually limiting how much they explore each of these barriers, or often not even doing most of them. And so almost no simulations use these more expensive detailed simulations, and most don't even explore most of the other barriers. And so this is why sometimes when I do gravitational paleontology, I feel a little bit like this guy, where just like running over track and just like falling into hurdles over and over again, without maybe becoming first on the track. And so I think it's a very honest and good question to ask, like with so many uncertainties going on, like should we just give up and stop doing this research, or is there a way to maybe understand all these like uncertainties on top of uncertainties on top of uncertainties? Okay, so what I'll try to do is that we're working really hard, including me, to try to see if there's hope, but also like to really overcome these barriers. And the first step to do that is to really start quantifying. First of all, like what are the barriers? Like how important are they? How important are these uncertainties? How much do they impact our results? And then to try to like improve on them and really replace some of these barriers or get rid of them by improving our simulations. So I just want to share with you in the rest of the talk, like some of the ways that what my group and other people have been doing this in the past few years. And this is very recent, right? So the field has completely changed since first detection in 2015 to like, now we have a problem that we want to improve our simulations and they're already behind like the observations. So it's very exciting. Okay, so let's go to the first one, this uncertain information channels. So I told you there's like all these different like formation channels with these different colors. And so the first thing that I was excited to do is to just see like, okay, if you just look at all these different formation channels, do they all, now that we have binary black hole neutron star, and binary neutron star mergers, do they all actually produce the right rates? And so what you're going to see, if you pay attention in the next 5 minutes, is actually an overview of more than 200 papers in the past 10 years. So a lot of papers you will read in just a few seconds. And what you will see is that on this x-axis, I have plotted what I call like the local black hole merger rate. So it's basically how many black holes are colliding per year, per gigaparsec cube, so per volume. And in this case for binary black holes, but we'll also show it for black hole neutron stars. And these 4 data points are actually what we know from observations. So what LIGO does, LIGO and Virgo, they have now seen about 100 gravitational wave detections from binary black holes. They know to which volume they're sensitive to, and they know for how long they've been looking. And so from that, they can calculate how many binary black holes will we see per year per gigaparsec volume. And they have 4 different estimates. So these are median and then 90% credible intervals. And you'll see that they all kind of lie between 10 and 100 black hole collisions per year per gigaparsec cube. That's what we know today from these 100 gravitational waves. And there's 4 different data points because there's kind of 4 different assumptions that the collaboration made about mostly the underlying mass distribution. So what are the masses of black holes, especially the ones that you don't see that come into this. Now it will flip through this video where now it will show you all the theoretical predictions. So here each color represents one of these formation channels. They come from pairs of massive stars. And now each line represents like one PhD student or like one professor who like sweated and like did a lot of hard work to like run these simulations. And so they ran like a big populations of massive stars from one of the formation channels, calculated like how many form gravitational wave sources given their assumptions. And that forms like one scatter point in this large horizontal line. And then if you see what I did is like, sometimes they rerun their simulation with slightly different assumptions. And if that's the case, I connected those scatter points with like a line. So this is like one simulation with different assumptions and then connected. And now this is for black hole neutron star. And so you'll see there's like observations and then there's like all these different formation channels. And what you'll see is like a couple of things. So there's some formation channels that maybe don't reach the observational data. But you also see that actually most formation channels, so most different colors, do kind of reach and this possible limit. So possibly all these formation channels could produce all the black hole neutron stars or all the binary neutron stars or all the binary black holes that we see today. And for binary neutron stars is cool because not only do we have gravitational wave data, but we also have all these other electromagnetic data, such as pulsar binaries that kind of lie near each other. But the other thing that you'll see is that there are actually like huge ranges between these points. So like many of these formation channels easily span like 4 or 5 orders of magnitude in this diagram, especially when you include different models and different simulations, different papers. And so one of the other things that we found is that actually when you just look at these local merger rates, so this is the merger rate at redshift 0, like near us, that just comparing the rates from simulations to observations is not really going to lead you to an answer. It might maybe exclude a few channels for black hole neutron stars and binary neutron stars, but in most cases, it's really difficult to like tell, okay, now this is the formation channel that wins or is ruled out. And so this is challenging, but then with the student, one of the things that we were doing is that like, okay, but maybe this is, when you look at redshift 0, which is here, like maybe there, you can basically really get very different values for the merger rate if you like vary these simulations and these parameters. But maybe the shape of the distribution, so kind of like how does it behave and where does it peak, for instance, and what is the slope before and after the peak, maybe those are very similar even when you vary some of these simulations. So that's something that Adam Bowski, a student, is investigating now for the specific formation channel where they come from massive pairs of stars, where he indeed found that like, okay, there's some small differences and it doesn't exactly follow the star formation rate, interestingly enough, but overall the shape is relatively similar between all these simulations, where you see that the peak is, maybe deviates like 1 redshift, but it's kind of around redshift, between redshift 1 and redshift 3, and then always kind of behaves somewhat similar to this. And this is interesting because then what we're working on now is like, okay, so maybe we shouldn't just look at the local merger rate, but maybe if you indeed add this dimension of what about the merger rate as a function of redshift, you can start seeing these differences, in this case, between different formation channels. And so one thing I'm working now on with my group is like to actually make a big catalog of all these formation channels, but then for the rate as a function of redshift, and also looking at other dimensions like masses and other properties as a function of redshift, where you start seeing that like, yeah, maybe this is like for gravitational waves coming from massive pairs of stars. This is for population 3 stars, so maybe there the peak is later, and this is like for globular clusters, so you see like a sharper drop off. But again, it's important to consider like other simulations with other parameters because there will be like some variation. And so if you do that, you get a picture like this where, you still see differences between formation channels, but they become a little bit more blurry. So it's going to be really interesting to see if from observations we can tell these models apart and learn something. Okay, the other barrier is that the initial conditions are uncertain. And so there's a lot of people now looking into this because we're also really, really interested in, can we use gravitational waves to actually probe things like star formation or metallicity and initial conditions of massive stars at like high redshift. This might be the only way. And so specifically what people have looked at is like looking at like, okay, if you change these initial conditions, so you change what we call the star formation history of stars, and especially the metallicity distribution that these stars form with, how does it impact the actual gravitational wave observations? And so there's a lot of work done, including by Martina Kraslinska, and here's, for instance, Max Brill, where they look at like, okay, if we have these different assumptions, these different lines for what our universe look like and how they produce stars through redshift, through cosmic time, does it leave a different imprint on, for instance, the binary black hole merger rate? And so we might actually be able to tell apart and learn something about the universe and star formation from gravitational waves, which I think is very exciting. People have also done this for like now other formation channels. So for instance, this is population 3 stars, which have very uncertain formation histories. And so the hope is really that with future detectors that might be able to observe these gravitational waves from population 3 stars, that we hopefully might learn something about star formation, but still a lot of work to do. And so, for instance, one of the things that another student of mine is doing with a team from CCA is to actually use these big camel simulations, which is a big set of more than 2,000 different cosmological simulations, to explore how like even different parameters in these cosmological simulations, like impacts, and explore that parameter space of simulations and star formation history, which I think is very interesting. Okay, they are also rare, these gravitational wave sources. So that's like a big uncertainty in producing a lot of gravitational wave sources. And so one of the other things I'm very interested in, more on the AI side and statistics side, is to improve our simulation. So one of the things I did, which is maybe the funniest thing to show, is I developed a new algorithm that I called Stroopwafel, which basically is based on this adaptive importance sampling, which is like an adaptive sampling technique. But actually the easiest way to explain it, I find, is like to say like, it's actually very similar to how you would play a game of battleships. And so for those of you who don't know, in a game of battleships, you're basically trying to like find the location of like 8 ships that your opponent has placed in this like 2-dimensional grid of space. And so in our case, we do something very similar. And so in principle, when you play a a game of battleships, you could play it in very boring ways by just like randomly guessing each time like a new location in the grid. And then, you know, sometimes it will be a miss and sometimes it will be a hit. But probably if I ask most of you, the way that you play this is actually that, okay, maybe in the beginning you guess randomly, but then once you find a hit, you actually explore and refine around it. And not only is this, you know, more fun and less boring way to play the game, it actually turns out if you do the real Python simulation of a game of battleships, but this is much faster. So you actually find all these ships on average in 65 tries, where otherwise you would need like 97 out of 100 possible tries to find all the ships. And so in our simulation is very similar, but instead of, you know, looking for ships in this two-dimensional grid, we're actually looking for the pairs, the initial conditions of stars. So for instance, the initial mass combination of stars that will lead to a gravitational wave source. So now these like ships or islands are the pairs of massive stars with the right conditions, such that they actually form a black hole pair that can collide and form a gravitational wave source. The only thing is, it's not as easy as playing a game of battleships, because you have to imagine that like this parameter space is much larger, like 10 or 12 dimensions. These ships, they only basically are 1/1,000,000th of the parameter space or 1,000th of the parameter space, because they're so rare. It's such a rare outcome. And you also don't know beforehand like where they are, what the location is, but also what the size of these ships might be beforehand. And it might well be that in a simulation there were no ships at all in that specific case. But we still did this and called this stroopwafel, and especially now with a group of students, we're actually improving this code so that it even works in like this 10-dimensional parameter spaces, which can be pretty challenging. And by doing so, and by using this like adaptive like mesh refinement like technique, you can actually speed up these codes by more than a factor 100. So it basically means that simulations that before took about a year to complete now can be completed in just like 4 days. So it's a huge increase on our side. Okay, now last but not least, one of the other things that's important is to also look at like stellar evolution and like how these different uncertainties in both stellar evolution and not knowing how stars exactly are formed like actually impacts your gravitational wave results. So one of the things I'll show here is that, again, you can, the first thing that's easiest to look at is just like this local merger rate. So here, I'll show you for black hole neutron stars. This green bar shows you the rate of black hole neutron star mergers at redshift 0 per year per gigaparsec cube. And so now from the about 3 black hole neutron stars that we have observed, we know it lies somewhere between like 50 and a bit more than 100, like 200, 300 black hole neutron star mergers per year. And so before, because computational time was very limited, what people would do is like maybe run one simulation or like 1 or 2 simulations. And so something that you would find is maybe something like this, that your simulation point is somewhere here. And okay, it's like consistent with observations, but that's it. And so one thing that we did now that we had this code to speed up our simulations was actually to like understand how do these different uncertainties like impact the outcome and like the rate that you expect of black hole neutron star mergers. So that's what this shows. So now what you'll see is that like basically as you go on this axis, like all these different letters represent different simulations that assume different like assumptions for the stellar evolution parameters. So things like mass transfer, wind loss, etc. Whereas if you go vertically in this direction, it actually explores different like initial conditions. So for instance, different star formation rates in our universe. And so something that we found by doing this large grid of simulations is that this outcome of the simulations and what rate of black hole neutron stars you expect is actually like drastically impacted by both stellar evolution uncertainties and these initial conditions uncertainties. And so that's important to understand and to quantify, especially now that we have and can run these larger simulations. And this is also true, and you can do the same game basically for binary black holes, where we see it's like much flatter. So it's much more impacted by basically different star formation rate densities and assumptions for your metallicity distributions than for the stellar evolution. Whereas if we do the same game for binary neutron star mergers, we actually find that it's almost not impacted by these like initial conditions, and much more impacted by stellar evolution. And this is something that actually now that other codes have started to do the same, many different codes find that there's different behavior for these different flavors of gravitational wave sources. And we think it reduces back to these effects that basically how easy it is to form gravitational wave sources from stars as a function of metallicity, like the metallicity that you start with. For binary black hole, had this like sharp decrease. As you go to higher metallicity, almost no stars form binary black hole mergers. Whereas for binary neutron stars, we have this much more like horizontal effect, where like it's almost not so sensitive to metallicity. And so we're hoping that some of these, what we think are more robust findings among the chaos and uncertainty, can help us with understanding all these like different formation channels and challenges. And I have another student actually working on this, like also trying to find kind of things that are consistent predictions, even when you vary uncertainties, which are here different lines, but then looking at not just the rate, but also like properties of the binary black holes and black hole neutron stars. So this is the most massive black hole of the binary. Okay, then last but not least, there's also a lot of work being done to really eventually go to more detailed simulations and replace some of our too simple and parameterized prescriptions by more detailed prescriptions. And one of the biggest one in this area is that actually almost all codes today that do this population synthesis still rely on SSE and BSE. So this is single star evolution and binary star evolution, which is a paper by Jared Hurley, basically from 2001 and 2002. Since then, so this is basically that describes the algorithms and the stellar grids for single star evolution, and then the basically the interactions between stars, so the binary interaction prescriptions. But we have learned a lot since the 2000s, especially our simulations have improved a lot. So there's a lot of work being done to basically replace, for instance, these single stellar evolution grids, which you can see here are fairly simplified by more detailed stellar evolution grids, like made by, for instance, MESA models, such as the one that Mathieu makes here. And so there's, for instance, a group of Poseidon, but also Matisse and codes that combine that try to really get rid of this like older code that might not be as representative and replace it by this newer grids, but it takes a lot of time. So it's work undergoing. And there's a lot of people that, for instance, show that which grid you use can actually have a drastic effect. For instance, here, different colors say like what is the formation history, or like what mass transfer phases did it go through during its evolution. So it really might matter which grid you use. So there's a lot of people investigating that. And so overall, the hope is really that maybe today we're kind of falling over these uncertainties, but then in the future, like with a lot of this help that I'm doing, but also other groups in this field are doing, that we can soon kind of go to this like right-hand picture where we're better understanding and trained to understand all these uncertainties and have quantified them so that we're better at like overcoming them, hopefully replacing some of the barriers by better simulations. And so eventually can make better stellar evolution models that can predict these different formation channels, simulate them, and compare them to observations. And so that will hopefully in the coming years go through a lot of revolution, so we can really start doing this picture of forward modeling stars and understanding what gravitational wave sources they form. And that's good because at the same time, there's people working on also trying to get a better understanding of how to go, basically do the other way around, how to go from already the gravitational wave observations to understand stars. And so hopefully together, especially in a few years, we'll like complete this picture. And there's a lot that I can say about that, but just to give a few examples, there's also like things we can learn already now about massive stars and these formation channels from just the observations that we have. And so to give a few examples that for instance, we're finding black hole collisions that have black hole masses that are in this so-called upper mass gap, where we actually think from just pairs of massive stars or black holes that directly form from the collapse of stars, that we don't think black holes should exist because they should completely explode, like the stars that make such massive black holes completely explode and don't leave a black hole behind. And so the fact that we're seeing a small but non-negligible population here might already hint and make people argue that maybe at least 10% of all the binary black hole collisions that we see today don't come from just pairs of massive stars, but for instance, from this like dynamical channel, where you can have two black holes collide, form, for instance, an 80 solar mass black hole, and then collide with another black hole. And maybe that's how you form these black holes in the mass gap that wouldn't violate this other theory. There's other hints that actually direct towards the other direction, which is that, for instance, you can look at the spins of these binary black holes. Now, gravitational waves, you don't directly measure the individual spins, but you measure the spin that we call the chi-effective or effective spin. And so it's a mass and spin orientation weighted spin. And the most important thing is that if both spins of both black holes are maximum and aligned with the orbit, you would expect the chi-effective of 1. So it's like here. If they were both misaligned and maximum, you would expect chi-effective of -1. And if it's near 0, it basically means the spins are either like misaligned like this, or they're like kind of small in magnitude. And so what they're finding is that, like, first of all, maybe many of the black holes actually have low spin. So that's why a lot of them are kind of around 0, but that there's this slight preference for like a distribution that's relatively positive overall. So there's like a small percentage negative, but a relatively positive. And this means that if they all form like randomly in these globular random dynamics, then you would expect actually almost a perfect Gaussian. So this hints that like maybe the formation channel that produces at least 80% of the binaries has like a preference for aligned spin, which for instance could hint towards massive stars, pairs of massive stars that are contributing this. And so another hint that is kind of telling you something about how these systems formed. And there's more work being done. So again, with 100 detections, you cannot do that much yet, but there's people starting to kind of see if just from the gravitational wave data, can you kind of find these clusters of populations. And so there was a recent paper that, for instance, argued that maybe there's hints for a kind of one population with low mass black holes and low spin, positive spin, and one population from observations with like higher masses and sometimes like lower spin or higher spin, which could also mean like maybe these come from these pairs of massive stars and these come from a more dynamical channel. So there's hints from observations that we might be able to learn and tell populations apart that will help us. Now, most excitingly is that we really need to do more work in this because it might be really hard work to overcome all these barriers, but it will be really, really worth it. And that's because of this picture. So this is going to be an animation that will show as a function of time the number of gravitational wave detections that we have detected or expect to detect with upcoming and future detector runs and observations. So first of all, it starts here. And now in 03, we have about 100 detections. But then 04 is running basically right now. It just stopped for a month and will continue for another half year. And then we have 05, which is another run of like LIGO Virgo at higher sensitivity. And then these are basically like improved detectors. So Voyager, or sometimes called A-sharp, are basically the best, most improved LIGO Virgo detectors with like better mirror coding, et cetera, et cetera. So it again increases like factor 10 or 100 the number of observations. And then Cosmic Explorer and Einstein Telescope are these next generation detectors that we're discussing right now and hoping to build, that are gonna have much longer arms, maybe gonna be underground. And by doing so, they can really improve the number of detections to basically seeing 100,000 or many hundreds of thousands black hole collisions, black hole neutron star collisions, and binary neutron star collisions per year. That's really exciting. And one of the most cool thing that I hope we can use it for is that, you know, if we translate this to like, you know, okay, every gravitational wave source informs us maybe about 2 massive stars, so that would really come down with like a $1 billion cost for a single detector to like $100 per massive star information, which is relatively cheap compared to like Hubble orbits, many Hubble orbits that we sometimes use to like look at one star or so. So, you know, but again, in order to do that and to make this picture, we really need to like understand how we can use this these observations to learn about massive stars. The thing I'm most excited about is that it's not just going to detect more things, it's going to detect it to higher redshift. So if you, for instance, look at like for LIGO, for binary black holes, say between 10 and like 100 or 1,000 solar masses, then currently LIGO is sensitive to redshift 1. So the first thing we've seen is kind of redshift 1, 1.5. But these future detectors are going to be sensitive basically beyond redshift 10. And so in case you hadn't realized it, these detectors are really estimated and predicted to basically detect every single black hole collision that's happening in the universe, at least until redshift 10, and possibly a few beyond, as long as they're out there. And so it's going to be like the most complete sample you can ever dream of, especially as an astronomer, massive star astronomer, where you often have to deal with like incomplete samples. This is like really, really wonderful. And on top of that, there's so much more cool things that I don't have time to talk about. But on top of that, for instance, there are going to be many other detectors, especially also here, that might detect double white dwarf or other black hole neutron stars or binary black hole binaries, such as LISA or DECIGO. And of course, we're also going to learn about black holes on different scales, or for instance, a stellar mass black hole colliding with a supermassive black hole from even different detectors, such as the PTA, like the pulsar timing arrays. We can also measure like black hole background, etc. On top of that, if that's not enough of you, then the next era is also going to see a lot of like other observations, including electromagnetic observations. So think about like pulsar surveys that are going to increase. We're now seeing these Gaia black holes or black hole helium dwarf stars. Like there's a lot of super cool LSST and other observatories coming up also in the next like same time scales that are really going to further like increase our knowledge about how massive stars hopefully are born, live, and die. And so I really hope that all of those things will really help us improve understanding this picture of how do massive stars evolve and make it possible for us to like paint this picture of how they evolve and learn about how they die, which will then, with those observations, like really help us understand to go back from the gravitational wave sources to how did these stars once upon a time form, live, and die, not just nearby, but like throughout our cosmos, which will then hopefully like really tell us more about these massive stars, and especially tell us more about like how they produce and contribute to all these different astrophysical processes in our universe. And with that, I'll just tell you that like starting at Johns Hopkins in a year from now, we're going to actually hire a lot of people, including faculty actually in AI, through some initiatives. So if you're interested in that, please, I'm going to be here for another 1.5 months actually until the end of February. So please come say hi. I'm in office 333. I'm happy to talk more about that. And with that, I'll just say thank you.
Good questions, and I probably should find them one.
You can also
online, which I didn't. Do you also know where I could find them?
You can also run with this one if you want.
Sorry, is anyone else able to hear me? I thought they mic'd all these rooms.
Oh, okay.
At least the smaller room has a mic, but I'm not sure.
I can repeat the question.
So this is really nice work. I'm particularly interested in this this last goal that you highlight, your $100 per star of actually understanding formation pathways. And so I'm wondering about whether you've thought about applying this advanced sampling technique to basically the gradients of the parameters. So you show how you can zoom in on the regions where you actually produce the merger. But then when you go back to exploring the uncertain astrophysical parameters, you went back to kind of a grid search.
Yeah.
And so is there a way to apply this to, again, the gradients of your common envelope parameters, something like that? So you could focus, okay, here's where we actually need to explore because it has the most dramatic consequence on our.
Yeah, no, that's a really good question. And that's actually kind of some of the projects that we're working towards now, and project I'm working on, we're basically trying to make like, instead of indeed like a 1-by-1 parameter like change, we're trying to make this large grid of parameter values where then that would be really expensive if you did it for all the parameters and all the samples. So you can again like implement smart like AI, machine learning, or even sampling techniques where basically you can like emulate or predict the parameter outcome for one that you haven't tried. So we had a paper out doing this with like PCA, so parameter component analysis, and then we're thinking currently about like, are there better techniques? We haven't done it for these specific parameters, like these hyperparameters, because it's so expensive. So we're kind of waiting to like see, okay, which techniques will work, and like then decide on like, can we build this grid? But that takes a little bit more time because it's really, really expensive to build up a training sample, basically. We're currently doing on like some parameters that you kind of get for free. You get like, kind of post-processing parameters, we call them. And there we've tried to explore it. So we're hoping that like maybe with, if we see if it works for that project, we can actually do it on like the real parameters that we're interested in. But if you have any ideas for how to optimize that, or which techniques we should use on those kind of grids where you also have more like bifurcations or more like, on and off switches rather than like a uniform parameter range, I would love to like brainstorm on that.
Other questions?
Could you say something about why the binary black hole rate was so strongly dependent on metallicity? I mean, I assume that it's something to do with massive stars at high metallicity, but I'm curious about the specifics.
Yeah, that's a really good question. It was one of the first slides. But yeah, so basically what you're saying, there was like this plot I showed that showed, okay, if you vary the initial metallicity, then the black hole mass that you can produce like really changed from basically spanning this range between like a few solar masses black hole to a 40 solar mass black hole to like only between like 5 solar masses and 10. And so we think the main process is that like higher metallicity, so having more iron, so in your star to begin with, basically leads to stronger stellar winds. And so Nathan Smith, who works here, will like know everything about that. But so basically, like we think for massive stars, these winds are mostly driven by iron lines. So just that you have Fe with like many lines, your atom that can like jump back and forth. And so they can really like accelerate photons and material outwards and lose a lot of mass as a process of that. And so one of the direct results is that just because you lose so much mass, you might end up with like a smaller star or like less massive star that might not actually form a black hole, but maybe instead like a neutron star or normal star, like a white dwarf. But actually the main process that we also see is that these more mass loss through wind, for instance, also like widens the binary or has these kind of like other indirect effects that lead to like more binaries not being successful in like forming a very close compact object. Because it turns out it's actually really like you have to be really close at the end. Like, you know, you have to be like a few solar radii apart as black holes to merge in a Hubble time, like within the age of the universe. So yeah, if you have like winds that like widen you too much, that's actually already a way to kill or like not form successfully these stars.
Thanks.
That's a really good question.
Floor. Somebody is online, they have to shout because we have no way to see the chat. Yeah, I can ask you one in the meantime. Like when you showed the plot showing the rates as a function of, I believe it was redshift with different channels, your globular clusters were basically at the peak at redshift 2 equal to the angulated binary channel formations, and then then you show that there is larger uncertainties. So
Yeah.
everything. But what were those two baseline models? The rate, where do you get the globular clusters
Oh, like
from?
one of them is from like Carl Rodriguez.
Okay.
Yeah, and so the peak, so actually for globular clusters, it's very uncertain like where the peak of the like merger rate for binary black holes is, but like, and especially almost all globular cluster simulations still use the same history of like the same globular cluster formation history. So like where and when and how long does it take to form globular clusters? But it's usually based on like, oh, the cluster first has to core collapse. So that's like why basically beyond redshift 4, you don't really have a significant contribution from this channel where exactly that happens is debated. You first need to form these clusters and core collapse them and then still collapse
So
them.
that was not including the contribution, the potential contribution of open clusters.
No, that's a different one. That's not included in this one. Yeah, that's a good point.
I'm curious, in addition to the merger rate that you show in from LIGO data, would studying like the mass distribution of all LIGO detection we've seen be helpful in constraining the formation and evolution pathways?
Yeah, and that's exactly also like a project that I'm now asking funding for and like hoping to complete in the coming years. Where like I think one thing that's becoming clear is that, you know, we look at local merger rates and that's really not so informative. That's just like one number at redshift 0, like how many things merge. It's just very easy to, you know, tweak one parameter and get that. Merger rate as a function of redshift is already a bit more telling, but I think especially like things like mass distribution, spin distributions, and then especially mass distribution as a function of redshift will be very informative. The challenge is like with 100 detections, we have some information about the mass distribution, but it's still uncertain. But I hope that like with 04, 05, once you have like 1,000 detections, we can really start learning about more detail of the mass distribution. And from there, we're also a bit behind it. Like currently there doesn't exist that much literature really comparing many simulation mass, like the complete mass distribution for many different simulations, but I hope I can produce that like in the coming years. Yeah, so hopefully at the same time.
Yeah, so I understand that there is a lot of uncertainty here because of all the different steps that they're not necessarily fully understood and everything. But I was wondering, so assuming that my model is perfect, how do things look in terms of like degeneracy? So like if I give you or whatever, if I have a gravitational wave waveform, how many options, like how many different parameterizations can I find, even if I assume that my models are perfect? How much can I restrict the evolutionary path of the star?
Yeah, no, that's a really good question, and like in similar way that like a lot of people have rephrased that question is kind of like, what is going to be more informative, to just find like 100 binary black holes, or like to find one binary black hole that's really difficult to explain with many other information channels? And we're already seeing it now, where many of the maybe black hole mergers that we see, like any formation channel can maybe, like most formation channels might maybe be able to produce, say, a 20 + 20 solar mass black hole collision. But there's some systems that we're already seeing now, and now it's like, okay, we see few, so people are still debating, is this a common thing, or were we just lucky to find something weird? Or people have a lot of challenges to produce it, maybe even with any channel. So to give an example, there was 1908-14, which is basically a gravitational wave source, but I think is a binary black hole, but actually I'm also in a bet where I say it's a black hole neutron star, so should be careful. Which is like a 2.6 or 2.8 solar mass black hole colliding with like a 20 solar mass black hole. And so it's a mass ratio of about 10. So the difference between the masses is like a factor 10. And so actually this one is pretty challenging to make in almost all formation channels. Like there's maybe if it's in an AGN disk, you could make it, because then you have kind of the smaller black hole like sweeping through the disk and colliding with the massive black hole. But like again, that's one of the most uncertain information channels. So it's actually and then it seems like we've seen more of those. Like we've seen more mergers now that have kind of mass ratio of 10 difference. And we've now also seen more with kind of a 2.8 solar mass black hole-ish black hole. So it's kind of like those are very, very informative, because they kind of challenge the most, like which formation channel makes them. Similarly, like we've also seen 1905-21, which is like the second binary black hole that we've seen ever, which is kind of a mass that's like around 70 solar masses. Like we're pretty sure it's like in this mass gap. So there again, it's like one of those things that, oh, from pairs of massive stars, it's quite difficult to like form this binary. So maybe this means, okay, at least X% of binary black holes needs to come from this other formation channel. So people are doing this calculation, but like, when it's like single event statistics, you can always, you can still wave it away and say like, maybe this is just one crazy system, very rare system in our simulations. But I'm very excited to see like the results from 04, because I think the new thing that it will say that we won't know from 03 is that it's especially going to say how common or rare these systems that we found in 03, so far with 100 detections, like I think with 300 detections, so in a year from now, we will see how common these are. And so I think that will be very, very informative. Yeah, I think we will know whether like black holes between 2.5 and 5 solar masses exist, like after 04 comes out.
I had a question about, well, not Stroop-Waffle only, but just kind of like adaptive sampling in general. So the idea I got of like Stroop-Waffle from your presentation was, that you're sort of considering the process that gives you results as like kind of a black box, and then you just put in random, the battleship analogy, like basically you're just doing that. But and then it seems like the basic assumption is that there's going to be somehow islands where you're more likely to gain hits. What I'm wondering is like the full version of this, like, is it based on the idea that like the regions where you have hits are always going to be compact in this high dimensional space in some way? Or is it like trying to learn, like, is it completely agnostic to such assumptions and it's trying to learn some information about what because like in Battleship, the reason I know to like start scanning is because I know what the battleships are supposed to be shaped like.
Yeah.
Right. And if they were shaped like in weird ways, like they were some crazy pattern that wasn't like completely like compact, I would still be able to say, oh, every two I should skip or something. So what I'm wondering is like, is this approach based on this compactness assumption, or is it something that it like learns iteratively just from the feedback, like which patterns are
Yeah.
Like, I'm curious about how much it tries to invert the operations versus how much it's agnostic to them.
No, that's a really good question, and it's actually it's like one reason why, like, okay, if it was just as simple as battleships, it would probably take a week to like write down an algorithm, especially if you know beforehand like how many ships there's gonna be and like what the size of these are. Instead, this took like, I mean, now it's like ongoing for like 3 or 4 years to really like optimize it. I mean, it's already working by its basic, but it's also one of the reasons why we first tried like Markov chain Monte Carlo, or like there's some of these like edge finding techniques and like that are well known in like mesh refinement, where you try to like find, if you know like you have a few islands, okay, just find the edges and then you're basically done, and you just do some interpolation within an island. And those actually didn't work because it actually turns out that our parameter space, our outcome parameter, it's not just like island, but it's like, so sometimes these islands are very small, but can still be very significant. So it's really important that you still find them even though they're small and don't miss them. But also sometimes it's not really like a nice compact island, but it's like kind of this island and then a lot of fuzzy scatter around it, which is really hard to capture with like Markov chain Monte Carlo techniques or these other kind of usually smarter or more beautiful or faster, like much more optimized techniques that just often get stuck on like a small local like minimum or maximum, and then cannot easily like find this kind of like fuzz in your distributions. So it's not resolved. Like, I'm sure there's still like optimization, but the way that we do it is like to therefore like go to this like import sampling is in some ways like almost the basics of Markov chain Monte Carlo, where you really just try to say, I want to give a little bit more weight to this like areas, and then we have Gaussians, but we like basically iterative optimize it in a way like where most work went in is to basically write an algorithm or condition that basically says, okay, but always explore enough like around it, so like allow for enough randomness to still basically find that scatter in like the non-well-behaved areas. And then we optimize it in a way that like we can kind of say, okay, we still want to do better. Like, we don't want to go to completely random because then you also miss information from like not finding those islands to begin with. But we also don't want to like zoom in too much, like what you would maybe do with Markov chain Monte Carlo, so that you kind of never find this scatter or fuzzy or like too small islands. And so there's a lot of statistics and like kind of like how to decide how to optimize that I'm happy to tell you in detail afterwards. Yeah. But yeah, we definitely had to like think a lot about, it's not going to be as perfect as battleship. So like, how do we still deal with that? Yeah.
On that note, we're out of time, but we still have one spot for. Let's thank Flor again.
Thank you.